Okay, so we're running a little bit early, but I think we'll just continue on. So I'm going to talk about sample prep for powder diffraction. There's a lot to consider in this, and I'm only going to go over a few parts of it. For a lot of things where you might be doing powder diffraction, you actually have essentially zero control over how you prepare the sample for the measurement, because the sample itself dictates a lot of how you have to prepare this. So if you think about something like a thin film that you're trying to grow, or if you want to watch an operando battery experiment, the preparation of the thing that you're scattering from is completely determined by making that thin film or by making an electrode for the battery that actually works. And so you really have sort of minimal control over what you can do to get good diffraction data relative to what makes the sample do the thing that it should be doing that you want to study. So I'm not going to talk about any of that. If you have questions, ask or come talk to me. But I'm going to talk more about if you have a bulk powder and you want to measure diffraction from that, how can you prepare that to give yourself the best chance of getting good, high-quality data? So some tools of the trade. These are some of the things that you might be using when you're trying to mount a bulk powder for measurement. You can mount it in a couple of different geometries. So you can do it in a capillary. So these are some very thin-walled glass capillaries that you can buy. The wall thickness is about 10 microns. They're quite fragile. You can get them in regular SLS glass. You can get them in a slightly higher quality borosilicate glass, or you can get them in quartz. The quartz ones are actually fairly strong and resistant to much higher temperatures, which can be interesting depending on what you're doing. You can also use Kapton. So these are a polymer capillary. You tend to buy them in sort of long lengths and cut them down to size. The glass ones are nice because they have sort of a large funnel on one end that makes it easier to get powder into it to start the whole process. The Kapton ones don't have that, and so scooping up powder with those very thin capillaries can be a little trickier, but you can do it. The other thing that you may do is if you don't want to measure it in a capillary geometry for whatever reason, you can measure it in a flat plate geometry. And so you sort of pack this down into a bed of powder, and typically it's good to do this on one of these zero background plates. So these are either silicon, which is the ones on the ends, or quartz, single crystals, which have been cut at a very specific orientation so that during a measurement for a powder, you actually never illuminate any of the Bragg peaks. Or if you do, the Bragg peaks go in some other direction that you're not looking in. And so because they're very high crystals, they have basically no diffuse scattering. All of the scattering goes into the Bragg peaks. And as long as you don't look where the Bragg peaks are, you basically get zero background. So these are very handy. We have a number of these around at the beamlines. You can get them with different, they have little wells in the middle of them that are sort of milled out. You can get them with different diameter wells, different depths for the well, kind of as you need. I'm not going to talk too much about how to load one of these. Those of you who are going to be on beamline 7.2 for the powder diffraction, I think you'll be doing some of this. But a couple of considerations that I just want to mention. One is, how do you pick the depth of that well? And this is sort of sample dependent, because if you're using one of these, you typically want to work in a theta 2 theta geometry so that the illuminated volume doesn't change. And that gives you very nice data. But the problem is that that theta 2 theta geometry sort of assumes an infinitely thick sample. So if you have something very light, something carbon-based, you actually need quite a bit of depth before it becomes infinitely thick. The X-rays will penetrate down to the bottom of that pretty easily. If it's something very heavy, like a silver complex or a gold complex or something of that nature, it can be quite thin, and the X-rays won't penetrate very deeply, and so then you can get away with less material because you don't need quite as much thickness to the sample. The other thing that you want to think about is if you have a flat plate sample, it should be flat. So the surface should be flat and as smooth as you can make it. And that's actually a very tricky bit, because the easiest way to make a nice, flat, smooth surface is to take something like a microscope slide and just smash it down on the top of your powder. And this will give you a very nice surface, but it's also about the worst thing you can possibly do in mounting a powder sample because it's almost guaranteed to give you some preferred orientation. So if your crystallites are not essentially spherical, if they have any kind of shape to them, smashing them down will cause them to orient. So if you think about if you have plate-like crystals and you just kind of mound them up and then you smash them down, they're all going to align so that the plates are horizontal. If you have needle-like crystals, it will do more or less the same thing. The needles are going to align horizontally when you smash it down. That's not a good powder. You're not going to end up with particularly good data because you're going to have a large amount of preferred orientation that you then have to include into your model, which you would rather avoid. You would rather not have to, you can model these things, but it's much better to avoid them in the data collection and the sample prep than to deal with them after the fact. There's a huge amount of discussion, and I actually recommend that you take a look at this. There's a thing called the Rietveld mailing list. It hasn't been very active lately, but maybe 5 years ago, and every few years this comes up of what is the best way of loading a flat plate sample to avoid preferred orientation? And you get some people with very, very strong opinions, happy to voice them in a public forum. And this is all on an email mailing list that is archived, and I definitely suggest that you Google it. It makes for some interesting reading, and you'll probably learn a little bit of something as well, although you will hear a lot of conflicting opinions about what the best method is. I am happy to measure things in a zero background plate. However, I prefer to measure things in a capillary anytime I can get away with it. And there are 2 reasons for that. Well, maybe more than 2. One is preferred orientation doesn't tend to be as big of a problem in a capillary. If you're just kind of letting powder flow down into the bottom of a capillary, it has to have a pretty dramatic crystallite shape before it's going to align in a certain way. And so you tend to get a good random orientation of your powder that way. It's also easy to spin a capillary while you measure it, which gives you a better powder average. It's the same idea as rocking, except taken to the extreme. So you can get very good powders out of that. It also requires less sample. You don't need very much to fill up a capillary. And after you've sealed it, it's just there. You can stick it in one of these little scintillation vials, and you have it forever. If you mount a powder into one of these zero background plates, when you're done, you have to dump it out, store the powder. That same sample can be remeasured, but not in the same way that you loaded it the first time. If you have a capillary, the capillary is not really changing over time, assuming your material is stable. It's also a good way of sealing your material, especially if you use one of the glass capillaries. You can seal it in a controlled environment. So if it's an air-sensitive sample, you can seal it inside of a glove box, and it will forever be in an inert atmosphere that way. So a couple of other tools, a mortar and pestle. This is great for grinding up your sample, or if you want to mix different powders together, this is a good way to do it to make sure you get a good homogeneous mixture of the powders. In order to seal, I'm going to talk about using, this is just some modeling clay, and this is just a regular Bic lighter. You can use both of these to seal the capillaries, not the lighter for the Kapton. It doesn't really melt. But for the glass ones, you can use a lighter. And then just some other tools, tweezers for handling the capillaries, spatula for dumping some powder out into the mortar and pestle, and then a little fine file, which is very useful. I tried to get a picture of this in action, but it turns out it requires 2 hands, and it's very difficult to do something that requires 2 hands and take a picture of it at the same time if you don't have some help, and I didn't. But this is a very useful thing for sort of working the powder down into the bottom of the capillary. So step 1, of course, is I have some powder, and I want to make sure that it's a good powder for measuring. And so there's a couple of things that you want to keep in mind. One, it should be a pretty fine powder. So if you look at this and sort of move it around, and you can see some sparkle from large crystallites. If you think about something like granulated sugar, you move it around, you can usually see it sparkle. That is bad. That means that you have crystals that are too large, really, for what you want. And so you should try to grind that up to make them smaller. Something that looks like powdered sugar is preferred. So it should actually be a pretty fine powder. And a general thing that you can do is if you can see sparkle, you should keep grinding it. There are other ways that you can do this as well. You can get a very fine set of sieves, and anything that passes through the finest sieve, which is going to be somewhere in the order of maybe 30 to 100 microns, if you have a very fine sieve, will go through, and that's usually a pretty good size. It might be a little bit on the big side, but it would be all right. And so you want to continue grinding. And depending on your sample, this can be either something that you can just grind and grind and grind, or it may be something that you want to be very careful about because you can actually induce changes in your sample this way. It's very difficult to grind something so fine that you start to see peak broadening, so that's generally not a concern. What is a concern is that the act of grinding, at that point you get some very high pressures and you get some elevated temperatures, and so you can actually induce phase transformation. And actually, in grad school, this was an interesting way that people prepared their samples. They were making what are called co-crystals. So this is something that's fairly big in the pharmaceutical industry. You can take two different small molecules that may both be drugs. One may be a drug and one may be something else that, for whatever reason, you like to administer together. And it turns out that if you mix two of them in a mortar and pestle and you grind them together, sometimes by adding a little drop of solvent as you do so, you actually form a new crystal structure that contains both molecules crystallized into one phase. And so you want to be very careful that if you're just trying to prepare a known sample, or a sample that you have for powder diffraction, that you're not making something new as you're going through this process. Another thing is sometimes your material will just kind of be clumped together. It may be a very fine powder like what this is, but you can see, maybe you can see, it's all sort of in large clumps. You want to break those up, and so sometimes you want to just do a very gentle grinding to kind of break up the clumps and get a finer distribution. And also, if your sample is something heavy, like I was saying, a heavy metal, you may want to dilute this with something light. And you have two choices. You can do something light that is amorphous, like some glass. That's not going to give you any extra diffraction peaks, but it is going to give you a constant background everywhere. That's not necessarily good. You want a low background. So what you probably actually are better off doing is adding something that is light and highly crystalline, because this will give you certain diffraction peaks, but everywhere where you don't have one of those diffraction peaks, the background is still low, and you can model whatever you dilute it with. And typically you want something of very high symmetry that leads to very few diffraction peaks. And so something like diamond powder is actually something that you might want to consider. It's diamond, and so you might think, oh, it's expensive, but you can actually get industrial diamond grit of pretty fine grit that works quite well for this. Boronitride is another thing that you can use. This is a common thing for the spectroscopy beamlines to dilute samples. We have a bunch of it in the labs here. Alumina is pretty good. This is also nice because it can give you kind of an internal standard if it's a very well-known material. And so if you know, for example, exactly what the lattice parameter of this is, you can be very sure that you can know the lattice parameter of your sample because you can calibrate it to what's already in the sample that you're measuring at the same time. If you put in something that has a very well-known thermal expansion, you can actually use this to calibrate the temperature of your sample and not just where the thermal couple that's close to your sample is reading. So you can actually get much more accurate temperatures this way using an internal standard. Okay, so if you want to fill a capillary, the first thing to think is that you actually don't need very much sample. So people often ask, how much material do you need to do a good powder diffraction measurement? Typically, people want this in something like milligrams. That's difficult because a milligram of something organic is a very different volume than a milligram of something like iron oxide. But if you think about the volume that you need, if you want to use a 0.5 millimeter diameter capillary, that's something that's pretty standard, you really only need to fill it up to a length of a couple of millimeters. And so you're not talking about really that much material to fill that volume. So what I'm showing here, this is the funnel end of one of those glass capillaries. I've scooped up a little bit of material. This is actually maybe a little bit more than what you'd want to start with. It's a good idea to start with a small amount, work it down to the bottom of the capillary, and then decide if you need a little bit more, scoop up some more, and work it down to the bottom of the capillary and fill it up in stages, because you can actually sort of reduce the chance that you're going to get a clump that gets stuck halfway down the capillary if you're working with small amounts at a time. Once you get a clump that you can't work down, you're kind of stuck, because now you have a little bit at the bottom of a capillary. Everything else is sort of stuck halfway up, which is not really what you would want to do. So this is going to be plenty of material, and it's really not that much. So here it is, kind of right after I've scooped it up. Some of it has already kind of worked its way down the funnel into the capillary itself. And now the trick is be very, very patient, be very, very careful, and work all of the powder down to the bottom of the capillary. And so you can see I've got a clump here that's working its way down, one here. I've got some that's already worked its way down pretty much to the bottom of the capillary. And this really just takes a lot of patience. It can be very frustrating. You can break a lot of capillaries, but just be patient, be as delicate as you can, and in time it will all work itself down. And so the two things that I typically do, I take one of those very fine files. I can hold the capillary, and you basically just drag the file across the capillary, and it's going to vibrate the capillary a little bit, and everything kind of works its way down. The other thing that you can do is take the capillary and just gently tap it onto the table, kind of pack things down as you go. What you want to end up with is a good powder bed at the bottom of the capillary that is as packed and as dense as you can make it. So by tapping it, you kind of pack it down. What you're going to end up with, even for a well-packed capillary, is about a 60% filling. So you're only going to get, if you know the density of your material, you're only going to get about a 60% density in that packed powder bed. That's just kind of the nature of how random packing works. And so once you have that, what I'm showing here, it's probably difficult to see. This is the end of the funnel here. You may see that. Some of the powder kind of stuck to the wall of the capillary, so it looks a little bit pink. Down here is the packed powder bed, and I've got almost an inch of packed capillary there, which is going to be plenty. And so now what I want to do is get rid of all of this part of the capillary. I don't need it, and I want to seal it somewhere in this area. And in this case, what I did is I flame sealed it. And all you do is take the lighter and move the capillary through the flame. It melts. The glass collapses on itself. It will seal. You take the other piece away, and you can see here the end result. So here's where I sealed it. This is kind of the end of the capillary, or end of the powder bed. I actually got this probably a little closer to the powder than I should have, and I ended up with a little bit of a lump of glass on the end here that you may be able to see. So this was not my finest work, but it definitely works. I have a good sealed capillary. So this is now in a controlled environment. As long as I don't crush that capillary, this sample should basically live forever. And they fit very nicely into these little scintillation vials, which are handy for then storing the capillaries. So a couple of notes. I flame sealed this one because it was glass. If I was using a quartz capillary, you can't do this. The flame will not be hot enough to melt the quartz. You need a much hotter torch. You can do it, but I would recommend, if you want to use quartz capillaries, flame sealing is probably not the way to go. Also, you can think of some obvious problems with doing a flame sealing. If I have an air-sensitive sample and I need to do this all inside of a glove box, my lighter is not going to work inside of a glove box, assuming that you have no oxygen in the glove box, which is kind of the point. Also, probably not something you want to bring into a glove box. So you can't do this inside of a glove box. If you have a sample that is very sensitive to temperature, you want to be very careful doing this, or you don't want to flame seal, because the sample doesn't necessarily get very warm when you do this, but it may get a little bit hot. The other thing is, if you're very sensitive to temperature or oxidation, if I'm flame sealing here away from the powder bed, I still have all of this powder that's kind of coated on the inside wall of the capillary. And if I get that very hot, it may change phase. And what might happen, and I've seen it happen, is if I change the phase of this little bit of powder that's on the wall, now I've kind of seeded the system with a different phase, and over time the entire thing may transform. Just because now I've introduced a different crystalline phase, I've nucleated something, that phase can grow if it's lower in energy than what I have here, and so I may have just destroyed my sample just by trying to seal the capillary. It's very difficult to sort of avoid this coating onto the wall, so this is something you want to consider before flame sealing. Having told you the issues, this is what I do 90% of the time. It's usually not really an issue, but you do want to think carefully about it and be kind of careful. Okay, so the other option then is to do clay sealing, and I actually very rarely do this, and so this was one of my first attempts. But basically, here's the capillary, and I've just broken the capillary. And it turns out you want to be kind of careful when you do this because the capillaries are quite fragile, and so it's easy to sort of get a lot of cracks along the length after you do this. I don't think I have a lot of advice on how to do this well. I think a lot of this is sort of an art that with time and some practice, you find what works for you that gives you the best success rate, and that's what you stick with. I'm happy to talk about my very limited experience in trying to break these capillaries cleanly, but I do not claim to be particularly good at it. So this one worked, although you may be able to see it's not a very clean break. I've got sort of a shard sticking out here. But what you would then want to do is fill up this broken end with clay. And what I have found to be the easiest thing is if you take the clay and sort of pinch it into a thin layer, and then instead of digging the capillary in and trying to scoop out some clay, you just punch it all the way through that layer. And I've done this a few times, so each one would have given me maybe a fifth of this amount of clay. But you punch it through and you leave a little plug of clay inside of the capillary. You can punch it through again and you double the amount of clay that you have. And then you keep doing that until it's basically pushed up against the end of your powder bed. And so here it is just stabbed through a little layer of clay. For the final one, it gives you a pretty clean result at the end. If the break is not clean and it's very cracked and delicate, it's probably just going to fall apart when you try to do this, which is why figuring out a good way of doing this breaking is an important step that I need more work on. So this is the end result. Sorry, in this case, the powder is white, but here's the end of the capillary. Here's where the powder ends, and then there's the clay plug. So again, I have roughly an inch of sample. This is a slightly thicker capillary. This is an inorganic molecule, so I can probably get away with that. And the reason that you want to pack the clay all the way down to be against the powder is that you want to spin the capillary. And if I have loose powder or room for the powder to move inside of the capillary as I spin it, it's probably going to flow around. And what you really want to avoid is that the powder flows in and out of the beam as you're making a measurement, because then your intensities just go up and down in a random way, and that's obviously going to cause some problems. You don't have to use clay. You can also use wax. You can melt the wax and sort of dip this in and then let it re-solidify. You can use epoxy, although be careful because some epoxies will sort of contract as they dry, and so you might actually break the capillary just by doing that sealing. Any other soft material that you want to use can be done the same way. Maybe think carefully about what it is and make sure that it's not going to do anything bad when it gets close to your sample. If you do this inside of a glove box, make sure that you're not bringing in something that contains a lot of water. But this is a fairly nice approach, and this is much more amenable to doing inside of a glove box for something that's air sensitive, although in the case of clay, I would wonder exactly how well sealed that end is. So probably fine to measure. If I then just let it sit out for a month, I would be a little bit skeptical, but I could easily be wrong on that as well. It may be quite good. If you do something like wax and you melt it, that should be a pretty good steel. Okay, I think that's where I end. So those of you who are doing high-resolution powder diffraction on beamline 2.1 today, you'll be doing a little bit of this. And then you'll basically figure out, once you have one of these capillaries, what you do with it, how you measure it. So that's about all that I have, but I'm happy to talk about any of this further if anybody has any questions. Very quiet. Oh, Hans, yes. Yes. Yeah, that's an excellent point. So one thing that I will mention also with these glass capillaries, they're not very consistent in their diameter. So even though this is a pack of 25 that are nominally 0.7 millimeter diameter, they're not all exactly the same diameter. They're not even all the same diameter along their length. You can see that some of them are a little bit more tapered than others if you look closely. And so if you're loading similar samples that maybe you've prepped in slightly different ways that are nominally the same thing, you're not measuring the same amount of material. And maybe that is something that you want, because maybe you want to compare accurate peak intensities from sample A to sample B of nominally the same material. So if you think that you've made some amount of amorphous material and you want to know how much crystalline material is in the sample, that's another good reason to use an internal standard. And you can actually buy from NIST, and I think Sigma Aldrich has them now as well, very well characterized alumina powder that is known to be nearly 100% crystalline. And so if you very carefully weigh out a known mass of alumina, the fully crystalline stuff, and a known mass of your sample, then when you do the refinement and then you mix it into a homogeneous mixture, you can basically correct for the difference in the total sample volume, because you know that the ratio of one phase, the alumina, to how much of your sample you put in. And so if your sample was only 50% crystalline, and then another sample is 100% crystalline, the relative intensities of your sample peaks to the alumina sample peaks will change. And so you can actually correct for the different volume of sample depending on where, if the capillary is tapered, where along the capillary you measure, or if you're just looking at slightly different thicknesses of capillaries, what that thickness is. So internal standards can be very useful for a number of things. Sometimes a good idea, sometimes not, but a very useful way to do certain things very carefully. Yeah, Ben. Yeah.
To try and like pack the powder more densely,
Mm-hmm.
is it possible that you might do it too much to the point where you have to start worrying about preferred orientations?
It can be. So yeah, so if you use a wire or something to basically push down into the capillary and pack the powder, you can start to induce preferred orientation. The way that pushing down on a powder makes preferred orientation is worst at the surface, either the top surface that you're actually pushing on or the back surface that you're pushing against. So I don't know necessarily how bad it is in a capillary, but the thing that I would suggest is measure away from the edges, and you're probably less prone to preferred orientation that way. But if you do measure close to the edge where you've been pushing on it, you probably will see some amount of preferred orientation because of the same effect, right? If you have an asymmetric crystallite shape and you start to push on it, it will want to orient a certain way to pack. But as you move away from that pressure point, it should sort of there are ways for that force and pressure to get relieved as you move further down into the powder bed. And so the further away from that you are, the less prone to that you should be.
Another question that might be related to the GSACS preparation. If you wanted to do powder samples for GSACS, would you use the zero background plate, or is that something you can even do?
Yes. So if you want to do, well, for GSACS, you're typically it depends on what angle you want to be at, right? Because for really grazing incidences where you want to be at, you know, 1/10 of a degree or something very, very small, the problem is that with a powder, you're going to have a pretty rough surface, incredibly rough relative to the kinds of roughnesses that Tim was talking about, where you're looking at sort of nanometer roughness or better. Here, you're probably talking about micron roughness. And so controlling your incidence angle on something that rough is very, very difficult. Now, if you want to be at sort of 1 or 2 degrees, you're probably okay, and you can work that way. You want to be very careful that you've prepared a nice, smooth surface, as smooth as you can. But if you want to work at really, really low angles, for a bulk powder like this, it doesn't really work because the roughness just kind of kills you. But yes, one of the zero background plates could definitely work for sort of a grazing incidence at kind of a few degree. That would be a good way to go. Yeah. Okay. Any other questions? All right. Then thank you.